Let's continue our discussion on the different types of amplifier operation. In the last video, we talked about the common emitter amplifier, discussed how it works, and how to analyze such circuits. We'll do the same for the common collector amplifier and the common base amplifier. Towards the end, we'll discuss what differential amplifiers are. Before we begin, I'd like to discuss a little bit about gain. We already know what the voltage gain is for the common emitter amplifier. Let's briefly take a look at the current gain and the power gain. As in the voltage gain, the current gain is defined as the output current divided by the input current. Since the output current is obtained at the collector terminal, the output current is then the collector current IC. The input current is given by the source current. The expression for the source current involves the total input resistance, which you already know incorporates the effect of the base current through the input base resistance. Thus, the expression shown is the overall current gain from the source to the output. The expression shown is for a single-stage amplifier. Thus, great care must be done in order to derive at the correct result. The overall power gain is simply the product of the overall voltage gain and the overall current gain. The next type of amplifier circuit is the common collector amplifier, or more commonly known as the emitter follower. It's also biased with a voltage divider circuit, but the output is taken from the emitter terminal. Thus, there is no bypass capacitor. The output voltage is just the product of the emitter current and the effective emitter resistance, R small e. The effective emitter resistance is the equivalent resistance of the parallel combination of the emitter resistance and the load resistance. The input voltage is just the product of the emitter current and the sum of the AC emitter resistance and the effective emitter resistance. Thus, we derive an expression for the voltage gain of the emitter follower after cancelling the emitter current from the numerator and the denominator. We first note that the gain is always less than 1. If R sub small e is very much greater than the AC emitter resistance, then we end up with a gain of 1 or unity gain. Secondly, since the output is taken at the emitter terminal, then there is no phase inversion. Recall that phase inversion occurs because the output at the collector terminal is taken from the difference of VCC and the output at the emitter terminal. Thus, the output simply follows the input with relatively no change in phase or amplitude, and thus the term emitter follower. If this is the case, then what is this type of circuit useful for? Well, emitter follower is characterized by a high input resistance. Thus, the circuit can be used as a buffer between the source voltage and the load circuit to minimize the loading effect of the load resistance. We can determine the input base resistance to be the base voltage divided by the base current. Since the collector current is equal to the base current multiplied by the AC beta parameter, and since the collector current is approximately equal to the emitter current, then the input base resistance is expressed as shown. We write the expression for the current gain to be the output current, which is the emitter current divided by the input current. The input current is just the input voltage divided by the total input resistance. The total input resistance includes the voltage divider resistances and the input bias resistance, input base resistance. Finally, we derive the expression of the power gain, which is just equal to the current gain since the voltage gain is just unity. Let's now consider this example. We are asked to determine the total input resistance of the emitter follower circuit. We are also asked to solve for the voltage, current, and power gains. The AC beta parameter is assumed to be 175. The capacitive reactances are also assumed to be negligible at the operating frequencies. To solve for the total input resistance, we first need to determine the equivalent resistance of the parallel resistances of RE and RL. and from there determine the input base resistance, which will be used to determine the total input resistance. However, to determine the input base resistance, we also need to determine the AC emitter resistance. This we solve from the DC component of the circuit. We begin by solving for the Thevenin voltage and resistance. We obtain it to be 7.39 volts and 13.3 kiloohms. Note that the Thevenin voltage is the same as the source voltage computed in the reference material. Thus, we can continue with the computation of determining the emitter current by simply dividing the emitter voltage by the emitter resistance and obtain 14.2 milliamperes. From there, we are able to solve for the AC emitter resistance and get 1.76 ohms. Now the question arises, why did we not use the equivalent parallel resistance of the emitter resistor and the load resistor, which is 235 ohms, since obviously there is some loading effect? Well, that's because of the coupling capacitor. The coupling capacitor blocks DC signal and the effect of the load resistor is therefore not seen. The obtained values for the parameters that required are shown. Now let's solve for the gains. We know that the voltage gain is unity, since R sub small e is much greater than the AC emitter resistance. This voltage gain is the gain at the emitter terminal with respect to the base terminal. Solving for the current gain, we would need an expression for the emitter current. The emitter current is of course the emitter voltage divided by the emitter resistance. Now the emitter voltage is obtained by multiplying the base voltage by the gain. The input current is nothing but the base voltage divided by the total input resistance. Plugging all that in and simplifying, we get the value of 43 for the current gain. This is also the value of the power gain since there is unity voltage gain. In terms of the power to the load, since RE and RL are equal, half of the power gain is distributed to the emitter resistor while half is for the load resistor. As we explained earlier, the main advantage of using the emitter follower circuit is a buffer connecting the low impedance input circuit to the comparatively moderate impedance output that would cause some loading effect to the input. This is because of the effect of the AC beta parameter, which increases the input impedance of the common emitter. We can see from the equation of the input base resistance that the AC beta parameter limits the maximum achievable input resistance we can get from the circuit. One way to boost input resistance is to use what is called a Darlington pair. In the Darlington pair circuit shown, the base input of the second transistor is the emitter output of the first transistor. The current gain in the first transistor is AC beta 1, while the gain in the second is AC beta 2. The effective gain is thus the product of these two AC beta parameters. The input base resistance still has the same expression, but the AC beta has increased significantly due to the coupling of the two transistors. In the circuit shown, the leftmost part of the figure is the common emitter amplifier with the given characteristics. It is connected to the speaker via the Darlington pair. The characteristics of the Darlington pair circuit are also given. The speaker has a very small load resistance. Let's first consider the common emitter amplifier. The voltage gain of the common emitter amplifier is given by the collector current divided by the AC emitter resistance, which in this case is 5 ohms. We initially need to recognize that this is a two-stage amplifier. Thus, the numerator R sub small c includes the collector resistance R capital C and the total input resistance of the Darlington emitter follower. The total input resistance is obtained from the voltage divider resistors R1 and R2 as well as the input base resistance. The input base resistance is obtained from the product of the square of the AC beta parameter and the sum of the AC emitter resistance of the Darlington emitter follower and the equivalent emitter resistance. The equivalent emitter resistance is just the equivalent parallel resistance of the emitter resistor and the load resistor of the speaker. Now, the AC emitter resistance can be obtained using the DC emitter current. And to solve for the DC emitter current, we first solve for the base voltage. The base voltage is computed from the given equation and is obtained to be 8.25 volts. The emitter current is then obtained by subtracting from the base current 2 times 0.7 volts and then dividing it by the emitter resistance. Again, we use only the emitter resistance and do not care about the load resistance since the coupling capacitor blocks the effect of the load resistance to the DC action of the emitter follower. We can now solve for the AC emitter resistance of the Darlington emitter follower circuit to be 80 milliohms. Let's now solve for the equivalent emitter resistance first. Solving gives us 5.87 ohms. Using the equation for the input base resistance and plugging in the obtained and given values, we have 59.5 kiloohms. The input total resistance can then be computed to be 6.16 kiloohms. Finally, we solve for the gain of the common emitter circuit to be 172. Alternatively, you can Devonize the circuit and show that the results are the same. You can do that as an exercise for yourself. To solve for the gain of the Darlington emitter follower circuit, we use the equation for the gain given as shown. Plugging in the obtained values, we get unity gain as expected, and the overall voltage gain is then about 170. If the Darlington emitter follower were not present, then the output signal sees both the collector resistance of 1 kilo ohm and the load resistance of 8 ohms. The effective collector resistance would then be 7.94 ohms and the gain would just be 1.59. We now see the significance of the Darlington emitter follower in maintaining the large voltage gain between the common emitter amplifier and the load, which is very, very small. The next circuit we're going to study is the common base amplifier. Again, we see that the transistor is biased with a voltage divider circuit. The base terminal is now connected to ground. The emitter terminal becomes the input and the output is taken from the collector terminal. The output voltage is the collector voltage and is seen as the product of the collector current and the equivalent collector resistance. The equivalent collector resistance is just the equivalent resistance of the parallel RC and RL resistors. The emitter voltage is the product of the emitter current and the equivalent resistance of the parallel AC emitter resistance and emitter resistor. They are now seen as parallel by the input AC signal since the input junction is between the AC emitter resistance and the emitter resistor. Since the collector and emitter currents are approximately equal, then the voltage gain is reduced to the expression derived. RE is typically much larger than the AC emitter resistance, and thus in this case, the input emitter resistance is approximately equal to the AC emitter resistance. Looking into the collector, we see that the output resistance is just the collector resistance. The current gain is obtained from the collector current divided by the emitter current, and since they are approximately equal, the current gain is unity. The power gain is then just equal to the voltage gain. As seen by the input AC signal, the input resistance at the emitter is given by the equation as shown. To find the input resistance and the voltage gain, we first need to find the AC emitter resistance. We Devonize the circuit and solve for the Thevenin voltage and resistance. We obtain them to be 1.76 volts and 9.88 kiloohms respectively. The emitter current is solved to be 1.02 milliamperes. We can now get the input resistance and obtain a value of 23.9 ohms. The voltage gain is also obtained to be 75.4. The current gain is unity, and the power gain is equal to the voltage gain of 75.4. Let's now talk about the differential amplifier. A differential amplifier is a type of amplifier that produces outputs based on the difference between the two input voltages. It has two modes of operation, the differential mode and the common mode. The differential mode is when we have two different input sources. When the input sources are the same, the common mode is the mode of operation. We'll talk more about the applications of this type of amplifier when we go to operational amplifiers. For now, we'll just try to understand how this works. The figure shown is that of a differential amplifier. It has two inputs and two outputs. The two inputs are the base terminals of the transistors, and the outputs are taken at each of the collector terminals. The collector terminals each have their own collector resistors, and they branch into a junction which is connected to a voltage source VCC. The emitter terminals also branch into a junction which goes to an emitter resistance and a voltage source negative VEE. When both input terminals are grounded, because of the negative potential at VEE, current at the emitter terminal increases, which also increases the collector current. When input 2 is grounded and input 1 is positively biased, the emitter current from Q1 increases. Thus, the collector current increases, and the voltage across resistor RC1 increases, and the collector voltage then decreases. Recall that the collector voltage VC is just equal to VCC minus the voltage across RC1. The emitter current from Q2 decreases since the emitter junction is at a higher potential. This decreases the collector current as well through RC2, which decreases the voltage across RC2, and consequently increases the collector voltage at Q2. The same behavior happens when input 1 is grounded and input 2 is positively biased, except that the collector voltage at Q2 decreases and the collector voltage at Q1 increases. Let's apply what we've learned about the basic operation of the differential amplifier to an input AC signal. If input 2 is grounded and input 1 is AC biased, then the output at the collector terminal at Q1 is the amplified AC voltage with a phase inversion. On the other hand, the output at the collector terminal at Q2 is the amplified AC voltage that is not phase inverted. If input 1 is grounded and input 2 is AC biased, then the output at the collector terminal at Q2 is the amplified AC voltage with phase inversion, and the output at the collector terminal at Q1 is the amplified AC voltage that is not phase inverted. This type of operation is a single-ended differential input operation. Here is where it gets really interesting. Let's consider two inputs, both AC signals at inputs 1 and 2, and each is 180 degrees out of phase with respect to each other. To figure out how this works, we first consider the case where we have input 1 and ground input 2, and take a look at the output. We then consider the second case when we have input 2 and input 1 is grounded, and take a look at the outputs. We then superimpose each result to get the final result. When input 2 is grounded and input 1 is present, the collector voltage at Q1 is phase inverted while at Q2 is uninverted. When input 1 is grounded and input 2 is present, where input 2 is 180 degrees out of phase with respect to input 1, then we have an output at Q2 that is phase inverted and output at Q1 that is uninverted. When we superimpose both results, we see that they add up and form a larger amplified signal. This type of operation is called a double-ended differential operation. Finally, let's consider the case when both inputs are in phase and take a look at the outputs. If we ground input 2 first and let input 1 be the input AC signal, then we have an inverted signal at the collector terminal of Q1 and an uninverted signal at the collector terminal of Q2. If we ground input 1 and then let input 2 have the input AC signal, then we have an inverted signal at the collector terminal of Q2 and an uninverted signal at the collector terminal of Q1. Superimposing both individual results gives us result 1 cancelling result 2. In other words, there's zero output at both output terminals because the signals cancel each other out. This action is called the common mode rejection and is typically used when you have unwanted signals appearing commonly on both differential amplifiers. I hope you've learned a great deal about how to use transistors as amplifiers using various types of biasing and transistor circuits. We'll take a look into the applications of differential amplifiers when we discuss operational amplifiers in our next lesson. It's now time to use this knowledge and apply it to a few example circuits in our reference materials. Whenever you're ready, you can begin with the third exam.